right?
Yeah.
Great. Okay, well, thank you for staying till one of the last talks, and I'll try to explain a few of the ideas we're following within the SAGES group, trying to understand the formation and evolution of galaxies, of early-type galaxies in particular, and by studying the stellar population properties. And since this is a very general question, I'll try to start with a very general introduction. So when you look at the spectrum of a massive, when you compare the spectrum of a massive galaxy, early-type galaxy, and a low-mass early-type galaxy in the local universe, you can already tell by eye that there are some features that are very different between one and the other. So you see, for example, that the H-beta line is much stronger in the low-mass galaxy, but when you go to iron lines or magnesium lines, you see that they are much weaker in the low-mass galaxy. So these are two galaxies, but when you do the same for many of them, you get this nice scaling relation when you find that the H-beta line gets weaker when you go to more massive galaxies, and you find that both iron and magnesium line they get stronger when you go to more and more massive galaxies. And you can try to quantify this and compare this measurement to your favorite stellar population synthesis models, and then you recover this sort of classical picture of early-type galaxy formation, where you have that more massive galaxies are older, more metal-rich, form more rapidly. That's why they have more enhanced magnesium over iron ratios. So this is great. This has been sort of the working picture over the last 10 years, and but this is all based on a very strong assumption, and that is that the IMF in this object, the stellar initial mass function in these objects, is the same as we observe in the Milky Way. I'm surprised we haven't heard that much about the IMF during this week, but the assumption we are making here is very strong because we are actually measuring the IMF in the Milky Way, something like this, but we are applying the same recipe to a galaxy like this. And the formation property and the physical conditions of the gas in this galaxy when these stars were formed are quite different to here. I mean, we have higher pressure, we have faster subformation rate, higher densities. So we have the environment was quite different here than here. So we have to be careful when using the same IMF in these objects and in these objects. Obviously, we cannot go there and count and actually measure the IMF as we do in the Milky Way. But we have two different ways to do the same in unresolved galaxies. The first one is to use the mass-to-light ratio as a proxy for the IMF. So, for example, if you steepen your IMF, if you include a lot of low-mass stars in your galaxy, and these stars are very dim, they do not contribute to the light of the, almost don't contribute to the light of your galaxy, but they dominate the mass budget. So if you increase the number of very low-mass stars, you're going to increase the mass-to-light ratio. And on the other hand, if you flatten your IMF, you're gonna decrease your mass-to-light ratio. So you can go to your galaxy and do a dynamical model, either via lensing or genes or whatever you want to do. You get your mass, take a picture, you get the luminosity, and that's the mass-to-light ratio. By using this mass-to-light ratio, you can sort of have a feeling of what's the IMF in your galaxy. The other approach, this is actually the one I've been mostly working on, is to look for spectral features that are different in the atmospheres of low-mass stars and massive stars. So in blue here, I'm showing the ratio between two stellar population models with same age, same metallicity, same abundance pattern, but with different IMF. And as you can see, there are, apart from a color term, there are some features that pop up when you change the IMF. So you can use this information, this spectral information, to actually go to your unresolved galaxies and constrain the shape of the IMF. We are working with early-type galaxies, which are usually very old systems. So we are limited to stars below, say, 1 solar mass. So we are not going all the way up in the stellar initial mass function. We have only this limited range. So it's a complicated task, but if you have good enough models, if you have good enough data, you can go and actually probe the IMF. And over the last 5, maybe 10 years, there's a growing evidence that the IMF actually is different in massive early-type galaxies than it is in the Milky Way. So we have here, this is the slope of the IMF. So steeper IMF, more low-mass stars here, and this is velocity dispersion, galaxy mass, whatever you want to put in. And with both methods, either dynamics or stellar population analysis, you recover this nice trend in the sense that when you go to more massive galaxies, you tend to have more low mass stars, but then when you go to less massive galaxies, you recover an IMF, which is more similar to what we have in the Milky Way. So yes, the IMF might be varying from galaxy to galaxy, but we really need to understand what is behind these IMF variations. So when you change from galaxy to galaxy, you are changing densities, you are changing metallicities, you are changing abundance pattern, you are changing many parameters. So to decouple this degeneracy, what we did was to, instead of looking for the integrated IMF of a galaxy, to do radial IMF variation, to look for radial IMF variations. Since you have different metallicity gradients, different abundance gradient, different sigma gradients at the end, when you compare your IMF variation, all these parameters are gonna decouple, and you are going to find, hopefully, you're gonna find what is the main parameter behind these IMF variations. And one of the projects we started was to using this nice Khalifa survey. So the idea was to go to the early-type galaxy region or sample in the Khalifa sample and calculate the radial velocity dispersion or V, RMS, H, metallicity, abundance pattern, and IMF profile. So we did calculated the gradients for all of these parameters for all our early-type galaxies in the sample, and we found that the only parameter that actually traces the IMF variations is metallicity. So these blue points here are not the integrated light from a whole galaxy, but individual points within different galaxies of the Khalifa sample. And we found that the local IMF measure, the value that we measure, traces the local metallicity. Oops, this is H, but actually this is metallicity, so the label is wrong. So the more metallic region of a galaxy is, the steeper IMF that is in this galaxy. And what is more interesting is that this not only works for our Khalifa sample, but when you put these red and yellowish points coming from our previous works, using different data sets, actually using different indices, you recover the same trend between IMF slope. Now here you have the metallicity. And even more, the dark points here, the black ones, are not resolved measurement within galaxies, but these are slow integrated spectra. So both local metallicity measurement and global metallicity measurement seem to trace the IMF variation. So great. We have something that sort of explains both the global and the local property variations of the IMF, but since this is a very difficult task, we want to be sure that we are actually measuring the IMF. And as I said at the beginning, we have two main proxies. To do this, I just was showing the stellar population analysis, but we can also do a comparison between the dynamical IMF and the stellar population IMF. So in the Khalifa sample, the good thing is that we can do this in a very homogeneous way, in the sense that using the same data set, same aperture, same everything, same models, we can compare in a very fair way, like apple to apples, the dynamical mass to light ratio in this case and the mass to light ratio we get from the stellar population analysis. So this is the first time it's done, and we did it in two ways. The first one was to use a single power law IMF, like Salpeter-like IMF, like a straight line through the whole mass range. And as you can see, there is sort of a correlation, so more steeper IMF or higher mass to light ratio in both stellar population and dynamical sites tend to agree. But there are many galaxies in this gray region, meaning that you have more stellar mass than dynamical mass, which is makes no sense. So what we also did was to use a more, more observationally motivated IMF, in the sense that instead of always increasing with decreasing galaxy stellar mass, it sort of breaks for low mass galaxies some sort of like Chabrier-like or Krupa-like shape for the IMF. And now you find that you have, now all the points here are compatible with sort of a physical solution, but you still get this relation between what you get from the dynamics and what you get from the stellar population analysis. So this is great, and this is not only telling telling us that both approaches are consistent, but we can, when you combine them, you can learn not only about the sort of raw shape of the slope of the IMF, but also about the actual shape of the IMF. So you can actually not only constrain the slope, but the shape itself of the IMF if you combine the stellar populations and the dynamic analysis. And now, great, we are getting more and more convinced that the IMF is actually varying in early type galaxies, but that means that we have one serious problem with the chemical enrichment of our galaxies. And you might say, okay, Nacho, you are just proving the low mass end of the IMF, and the massive stars are the one responsible for the chemical enrichment, so you shouldn't be very worried about this. Yes and no. I mean, yes, we are only proving the low mass end of the IMF, but there are two things. If you keep fixed, for example, the standard slope for the high mass end, you start, as you saw at the beginning, you start having problem with the mass to light ratio, because you have to put a really steep low mass end for the IMF. So that will give you very crazy mass to light ratio. So on the other hand, the massive galaxies are the one responsible for the chemical enrichment, but if you have a lot of low mass stars, there is going to be a lot of material, a lot of gas in your galaxy locked within these two very low mass stars that basically are gonna stay there forever. So you are becoming very, very inefficient in enriching your medium, because you are just locking all your material in form of very low mass stars that last forever. And when you do the numbers, you find that if you assume a very steep IMF, as we observe in the local universe for a massive galaxy, and you let your system evolve, there is no way you reach the high metallicities that we observe in massive galaxies. So a very steep IMF and a high metallicity that we observe in massive galaxies, they are not compatible. There's no way you match. I mean, you can reconcile both. And this is that really strong observable. We know these guys are very metal rich, and we know that they have steep IMF. So this is a very important constraint from the local universe. And the same sort of happens with the time scale problem with the magnesium over iron. So if you have a very steep IMF, you cannot. You need a very, very fast formation episode, extremely high star formation rate that we don't observe in the Milky Way, in the local universe. So the obvious solution for this is that either we have a really strong problem with all our star population synthesis model, all of them, and this is not only coming from the one that we use, but basically every model is using different approaches and getting the same steep IMF. So either there is a big problem with all our models, or the IMF has to vary with time. And so this is a really strong prediction from the local universe, but for example, our IMF metallicity relation is a way of sort of explaining this, because when you start to form a galaxy, you start from a very metal poor material that lead to a very flat IMF, which will enrich the medium, getting you a high metallicity and high abundance ratio. So the IMF metallicity relation we found is sort of a way of explaining this, but we really need to go to high C to really go and measure the IMF. And finally, I want to go back to this classical picture because, well, you can sort of understand how massive galaxies are old and how they are metal rich. How they were formed that fast, why didn't keep forming stars? That's, this quenching stuff is something that is not so easy to explain. And we decided to tackle this problem, also looking for the scatter in the black hole mass sigma relation. So what we did was to select galaxies from which we had black hole measurements and optical spectra to calculate the stellar population properties, and we divided our sample of galaxies into what we call overmassive black hole galaxies, those above the main sigma black hole, the best fitting black hole sigma relation, and those under massive black hole galaxies, those which at fixed velocity dispersion have a low black hole with a relatively low mass. And we tried to find if there were any difference in the stellar population properties of these galaxies. And we did find significant differences between those galaxies above and below the best fitting black hole sigma relation. So we found that at a given sigma, the galaxies above, those galaxies with more massive black hole tend to be older and tend to be more alpha enhanced. We don't know if this is a causal connection, but this is something that you would expect, for example, if the black hole is responsible for the quenching of the galaxies. So if you have a more massive black hole, that probably is fed a more intense AGN activity, which quenched faster and earlier your galaxy, and that's what you had: older edges and more enhanced abundance pattern. This is a summary. We found that there are radial IMF variation within early type galaxies. We found that the slope of this IMF is strongly correlated with the metallicity, with the local and global metallicities. We also find that the dynamical and circulation analysis of the IMF, they agree and they are compatible. And when you are analyzing the chemical evolution of your galaxy, you need to take into account that the IMF might be varying and might be varying following the metallicity. And also it might be also some sort of black hole feedback. And the final point is that I really want to make is that we really need to go to high redshift to the epoch where these massive galaxies were formed to try somehow, in a clever way, to try to measure the IMF of these guys when they were forming. Thank you.
For galaxies that are actually star forming, what would be the most robust way to get the IMF?
That's a good question. We have to think in a different way. We cannot go there and measure blindness or anything. This is at redshift 2. That makes no sense. Probably people have tried here in the local universe to use the H alpha to UV ratio, which is very tricky because these are completely dust obscure. But probably, if this metallicity IMF relation, it stands for at this high redshift, we don't need to go to this very dusty, already massive galaxies. We need to go to this sort of the pre-blue nugget phase where you do not have that much of dust and you can still use this sort of line ratio approach. And there are other things that we are still trying to find out. For example, the mismatch parameter that people from the dynamics use. In the local universe, the difference between in the local universe, for an old population, the difference between a steep and a flat IMF, it's like these mismatch parameters are around 4. But if you go to very young population, it goes up to 20 or something like that. So it's easier to distinguish a flat and a steep IMF at high redshift. From the stellar population point of view, obviously more difficult to get a reliable stellar dynamical analysis.
So the black hole result seemed pretty intriguing. What would happen if you just did the trends as a function of black hole mass alone?
What do you mean?
So you had.
The things that the IMF, the H and the abundance and the MGRF is a strong function of galaxy mass, so you cannot compare like the.
Right. But you had the black hole mass was getting larger as the sigma was. It just seemed as if they might line up with the black hole mass better than with velocity dispersion, rather than showing the split.
But yeah.
So it might be worth just looking at that plot just to see. And then a quick clarifying question, so metallicity, do you mean like total metallicity, or are you talking about Fe over H?
This is total metallicity. The models we're using, this is total metallicity. So this is including also the one.
Okay, well then I'm really confused because you had it solar, that the IMF looked non-Krupa-like, which is actually pretty weird.
That's what it says, but probably other parameters. It can be either like an offset between the models and the actual nature in there. Or maybe then I have really a strong feeling that there is something more apart from metallicity. That it's and in my view it might be density. The density might be playing a role to sort of as a secondary parameter to bring the solar metallicity to the solar IMF that we are observing.
Okay.
Yep, there's one in the back there. Run up there.
So this is really cool, but just to, I guess, go back to this IMF variation. So Marla Guija a couple of years ago looked at local ultrafaints, and she found that the IMF slope variation with metallicity was a lot weaker than what you're finding. I think it was consistent with what Krupa actually proposed back in 2001 of roughly 0.5 times Fe on H. Do you have any intuition about why the dependence on metallicity would be so different between your early type galaxies and the local ultrafaints?
Yeah, There are many things. There was this meeting in Baltimore like last summer, and the resolved and unresolved IMF groups were having like strong different opinions about this. But the things that they were focusing on very low mass. These are LEO satellites around the Milky Way, right? So in principle, it's not so easy to compare, and I can imagine many tricky things in there. I mean, they are low mass stars, so you might have like radial migration, you might have like mass segregation within their galaxy. So it's not super fair to compare what they are finding with, let's say, low number of stars with these very massive guys where you have like sort of central, the statistics are pretty higher in this case. But I don't really know. I mean, they find sort of the same trend like qualitative with more metal rich being steeper, but apart from that, the actual match is. Yeah.
Okay. All right. Thanks.
Let's thank Nacho again. And our last